Please, Shinji.
Yes. Okay, thank you very much. Okay, so yesterday, I think I talked about these 4, so up to section 4. So after introduction, I reviewed the general relativity and then the level of gravity. And then I introduced the PPN formalism, parameterized post-Newtonian formalism, and then the effective field theory of scalar tensor theory. So today, we are going to start from section 5, which is massive gravity. Then after that, Hoja-Lipschitz gravity, and then summary. And I'll try to be as pedagogical as possible, and instead of being historical. So, but okay, so let me start. So massive gravity. So the motivation for massive gravity have twofold, and originally, so the people try to answer this question. Okay, so the can we give mass to gravity, namely the spin to field? Okay, so this is a question, and so this is a question, fundamental question in the classical field theory. Okay, and I put here kind of a seesaw or a balance because the answer to this simple question turned out to be time dependent. So sometimes people say yes, sometimes no. So I put this. Okay, and the first answer was given by Pierre and Pauli in 1939, and they found a unique linear theory like this. And Lagrangian is given by some Einstein reduction that I introduced yesterday, and so expanded up to second order in perturbation. So the H is a perturbation of the metric around the Minkowski metric. Okay, and then we add additional term, which is graviton mass term, which is second order in H. Okay, like this. And possibly we have 2 terms like this or like this. This is a square of trace. This is a trace of the square. Okay, and the coefficient of these 2 ratio between coefficients of these 2 terms are fine-tuned to be -1 to avoid the so-called ghost instability, kind of instability. Okay, and so in this sense, this is unique. Okay, up to overall coefficient, which determines the mass of graviton. Okay, so once we fix the mass of graviton, then this is completely unique, up to second order at least. Okay, and this breaks diffeomorphism, and so that there is no momentum constraints that we discussed yesterday for GR and other theories of gravity. And fortunately, because of this structure, there is a kind of Hamilton constraint, but that is second class, and additional constraint appears. So but we don't have momentum constraint. So as a result, we have extra degree freedom. Okay, less constraint means more degree freedom. And in the end, we end up with 5 degrees freedom. Okay, 2 tensor and like a plus and cross modes of gravitational waves. On top of that, we have 2 vector perturbation and 1 scalar. Okay, so we end up with 5 degree freedom. Okay. So let me see that. Okay, so from this Lagrangian, we can get the equation of motion like this. So left-hand side is Einstein tensor expanded up to first order. Okay, in H, and right-hand side have 2 terms. One is contribution from this graviton mass term, and the other is a contribution from matter fields. Okay, T mu was introduced yesterday, and yesterday this was G rho sigma, and this was G. But we are interested in linear theory, so that we can set G mu nu to be eta mu. Okay. Minkowski background, and then this is a variation with respect to perturbation. Okay, and then we can compute the number of degree freedom in a simple way. Later we are going to do more complete, not complete, but some Hamilton analysis for nonlinear theory. But here for linear theory, this is very simple. Okay, so let's consider divergence of equation of motion. This one. Then the left-hand side vanish because of Bianchi identity, and the right-hand side this remains, but this vanishes because of the conservation equation of matter fields. Okay, I here assume that the matter Lagrangian matter action is invariant and coordinate transformation of space-time. Okay, so the conservation equation follows. Then we have just the divergence of this equals 0, and then we have this. Okay, from this we get actually from here this one we get this. From this we get this. Okay, and this is a 4 first-order differential equation, and we can consider this as a kind of constraints. Okay, and also the from the trace of equation motion. By using this equation, we get this. Okay, so indeed actually so the trace of this vanish if we use this, and also this also vanish. Okay, so we have only contribution from right hand side. Okay, so from here, trace give us just the trace of h mu nu, which is defined as h, and then from this we get this. Okay. With some coefficient. Okay, this is the algebraic equation. So this is also constraint. And let's consider vacuum, especially so this means that the trace of T mu nu, this is the trace of T mu nu, this is 0. Then in this case, H mu nu is transverse traceless. Okay, because this means that the trace is 0. And then if we set trace to be 0, then we have divergenceless condition, namely transverse. Okay. In the momentum space, we have this. So we have in the momentum space we have 4 plus 1 condition. So we have only 10 components. Starting from 10 components, we have 10 minus 4 minus 1, which is 5. So we have only 5 components. So we have just 5 degree of freedom. Okay, and this is what I meant here. Okay. And then we can look at the dispersion relation with T min equals 0 by considering kind of Fourier transformation. Okay, so this is so we have exponential ikx. In front of that, we have a polarization tensor. Then by plugging these two equation motion, we can obtain this kind of equation. Okay, so this indeed means that so mg, which is a coefficient of this term or this one, is gravitational mass. Okay. Okay, of course, this comes from this equation motion, which comes from this after setting these two equations. Okay. Now, so we have now unique linear theory without instabilities, but some years later in 1970, so so these people came up and they said that the massless limit of this theory does not agree with general relativity. Okay, so because we consider the Einstein reduction plus additional term, and if we set gravitational mass to be 0 from the beginning, we have general relativity. But if we have a non-zero mass and then send the mass to 0, send the limit where mass goes to 0, then the limit does not agree if we trust linear theory. So this is what they say. Okay. So let me show this. And from equation motion, by using these two equations that was derived here, this equation and this equation, okay, we get this equation. Okay, we can just take a linear combination of original equation and these two, and we get this. Then we Fourier transform. Then we have this equation in the Fourier space where T bar is the Fourier component of a stress energy tensor. Okay. Then we can solve this algebraically because this is in Fourier space. We can just divide this equation by this. Then the answer is like this. So this tensor is defined in this way in the Fourier space. So by then doing the inverse Fourier transformation, we get this kind of solution. Okay. So given source T mu nu, then in terms of Fourier transformation of the source, we can get H mu nu in the real space. Okay. In the case of massless theory, namely general relativity, we have this kind of expression. Okay, very similar, but difference. There are two differences. One is here. Instead of k square, we have k square plus mg square. Okay, because this is a massive theory. Okay, and the second difference is this coefficient. Okay, we have 1/3 instead of 1/2. Okay, so this leads to a big difference. Okay. And let's consider point source in real space like this. So we have only mass. So the 0, 0 component is non-zero, other components are 0, and at x equals 0. Then in the Fourier space, we have this. So that we can just plug this to this formula. Then we get this. Okay. And for 0, 0 component, for 0i component, it is 0. And ij component is non-zero because we have this term. Okay, this is 0 for ij component, but this is non-zero. Also, this is. Okay. So we have this result for ij component. And then using the formula of this inverse Fourier transformation, we get these results in the real space. Okay. And if we are interested in the small mass limit or distance larger than 1 over mass, then we can set this exponential to be 1. Then we get this result. Okay. And ij component, we have additional term here. But we can forget about this because this is a pure gauge. And but as I said, massive gravity doesn't have a diffeomorphism invariance. But here, I assume that matter action is a diffeomorphism invariant. So the matter cannot probe the difference due to this term. So we can throw away this term. Then this is equivalent to this expression. Then by considering the small mass limit or large radius limit, we get this result. And this is basically 1/2 of 0, 0 component. And this means that the ppn parameter that we defined yesterday is 1/2. Okay. Basically, the ppn parameter is a coefficient here. Okay. In the massless case, of course, we should have gamma equal 1 as we learned yesterday. General relativity has beta equal 1, gamma equal 1, and other ppn parameters are 0. Okay. And so let's see that. In the massless case, we have different Green function. And so for the same source, we have different expression. Okay. So the H00 have this expression, and the Hij have this expression. And for then the coefficient here is 1. So gamma equal 1, as it should be in the massless case. But in the massive case, we have 1/2, which is order 1 different. And indeed, as we have seen, the deviation of gamma from 1 is strongly constrained. And gamma equal 1/2 is completely ruled out by experiment. So however small gravitational mass is, the massive gravity would be excluded if the linear approximation is valid. Okay. So this is what they have shown. Okay. So the massless limit does not agree with a massless theory, which is GR, and this discontinuity is order 1. As a result, a massive gravity would be excluded. However, gravitational mass is small if the linear theory is valid. Fortunately, 2 years later, Weinstein came up, and so he showed that the linear theory breaks down in the limit. And so this is so-called Weinstein radius. Okay, so let's see that how linear approximation breaks down. Okay, so let's consider instead of linear theory some example of non-linear theory like this. So we have Einstein Hewitt action plus additional term, which is square of h mu nu, but this coefficient is some fixed metric. For example, we can set it to be eta mu nu as before. But here h mu nu is not, I mean, so consider the nonlinear field. Okay, so that this is fixed field, a fixed metric. And then here we have square root minus f. But then we can get the equation motion like this. And let's consider a spherical symmetric static ansatz like this for the fixed metric. So let's consider flat metric for simplicity as before. And then the G mu nu has 3 components: lapse and RR component and angular component. Okay. Then we can consider part of the expansion. Okay, epsilon is small, but we can go to higher order. Then the N and A and C are expanded in this way. At the first order, we get these equations from this equation motion. And then we can easily get a solution. Okay. But we want to consider a solution that is regular at large distance, x equal infinity, where x is a radius defined in this way, times gravitational mass. So this is dimensionless. And we can consider regular solution at infinity. So we throw away this. So we have just one term. At large distance, we have this kind of behavior, 1 over r. Okay. And we can substitute this to here and here to get A1 and A3, A1 and C1. Okay. Then we can go on to second order. And the second order solution is given by these expressions. Okay. This is the first order solution, and they are second order. So when this combination alpha over x to 5 is order 1, this expansion by perturbation breaks down. So linear perturbation breaks down because second order term becomes as important as first order. Okay. And at this moment, we don't know what alpha is, but we have already obtained the source solution in the linear theory, so that we can obtain alpha in terms of source. Okay. So for a given mass m, let me go back. Here we obtain H00 like this. So we know what alpha is. Okay. So alpha is given like this. Okay. So by plugging this to here, we see that if x is smaller than alpha to 1 over 5, then the perturbative expansion breaks down. By plugging expression of alpha to here, we get the boundary. Okay. So this is the so-called Weinstein radius. So if the radius is smaller than this so-called Weinstein radius, then the perturbative expansion breaks down. So this is good for massive gravity. I mean, for computation, it's not good because computation becomes a bit complicated. Okay? We need to take into account nonlinearity. But if we perform nonlinear analysis, then indeed the limit, massless limit agrees with general relativity. Basically, this means that if we ask the right question, then the physics is continuous as we change the parameter of the theory. Okay? So massless limit agrees with general relativity. But if we trust linear theory, then we have a discontinuity. Okay? Just nonlinearity saves the massive gravity. Okay? But there is some subtle point. The continuity is not uniform with respect to distance. For example, if we take 1 over r expansion, then it does not make sense, okay? Even if mass is very small. As for details of this Weinstein screening, please have a look at the review by these people. This is a very nice review. Okay. And anyway, so the answer changed from no to yes after 2 years. And then in this same year, 1972, actually the Borloo data came up, and indeed the answer changed to no. So they say that the same nonlinearity that saved the massive gravity caused a problem. Okay, so indeed because of nonlinearity, the Hamiltonian constraint that removed the extra degree freedom disappears then the extra degree freedom appears. And this extra degree is a ghost. So we have a 6 degree of freedom. One of them is a ghost, which leads to instability. Okay, so let's see how the extra degree freedom appears by doing some simple Hamiltonian analysis. Okay, so we have Hamiltonian like this. So this is the same as the Hamiltonian constraint in the general relativity that we have learned yesterday. And this is a momentum constraint, which is the same as the general relativity. Okay. And then we have additional term, which means that the pi n, which is this is a momentum conjugate to lapse, and this is a momentum conjugate to shift vector. They are vanishing, and lambda n and lambda I are Lagrange multipliers. Okay, we have additional terms. So up to here, Hamiltonian is the same as general relativity. We have already learned this, and this is additional term. Sorry, this is mg. Okay. Then we still have a primary constraints, pi n equals 0 and pi I equals 0. And then we should look at the consistency of these conditions. Okay, with respect to time evolution. Okay, yes, I have a question. Okay, why can't we have the mass term in? Okay, so yes. Here, I think the question is about this term. Okay, so if we introduce here g mu nu, then it leads to kind of mass term. Yes, but it doesn't vanish for g mu nu equal f mu nu. So we want to consider hf mu nu as a background, kind of background. So we want to make this to be vanishing at the g mu nu equal f mu nu. That's why. Okay. That's why we consider difference between two, then the square it. I hope this answers the question. Okay. If not, please ask later again. Okay. Okay, let's move on. And then we have these conditions because this condition should be consistent with time evolution, so that we compute the Poisson bracket between this and the Hamiltonian. Okay, same for pi I. Then we get these conditions. Okay, as you can see, these conditions can just determine n and nj. In this case, nj, because this matrix is non-degenerate. So in other words, if we compute the determinant of this matrix made of Poisson brackets between these constraints, this is non-zero. So we can solve these equations with respect to Lagrange multipliers, which means that all constraints are second class and there are no additional constraints. So we have just 4 from here and 4 from here. So we have 8 second class constraints. And as we have learned yesterday, each second class constraint removes one phase space dimension. So starting with 20, which is 10 times 2, 10 metric components times 2, minus 8 is 12. So the 12 phase space dimension means that we have a 6 degree of freedom. 5 is the same as the degree of freedom in linear theory, but we have 1 extra, which shows up at the nonlinear level. And this is indeed the ghost. Okay. And so the answer turned out to be no in this year, 1972. And since then, almost for 40 years, people believe that there's no way to give a mass to graviton. Okay, but there was some development, and the answer changed to yes recently. So let me explain this development. Okay, so in order to do that, the so-called Stickbell fields and the decoupling limit are useful, and these concepts are introduced in the context of mass to gravity by these people. Okay. And so we consider kind of nonlinear extension of this h mu nu. H mu nu is the difference between g mu nu and f mu nu. But so let's consider for simplicity f mu nu is the eta mu nu, which is Minkowski-metric. And so this is eta AB is a Minkowski-metric. And so we consider 4 scalar fields. Okay, this is just let's consider this just a matrix -1, 1, 1, 1, and then we introduce 4 scalar fields and then combine in this way, and then define capital H mu nu in this way. So the capital H mu nu is G mu nu minus this combination. If phi A is XA, then this reduced to indeed eta mu nu, because this part becomes just a Kronecker delta. This is Kronecker delta, so that this becomes this combination becomes eta mu nu. So the if phi A is XA, then the capital H mu nu is indeed H mu nu. But this is indeed covariant. Okay, so as we have learned yesterday, so indeed just diffeomorphism is a gauge invariant, gauge symmetry, and gauge symmetry is a kind of redundancy of description. So we can recover diffeomorphism by introducing redundant degree of freedom. So these so-called Stuckberg scalar fields are redundant degree of freedom. By introducing them, we can recover the diffeomorphism invariance. This is what they did. Okay. And then we can consider perturbation of phi around X. Then we consider 4 scalar fields. Okay, this is a kind of perturbation of phi. And in the context of effective field theory of scalar tensor theory, we learned kind of unitary gauge. This is a unitary gauge in the massive gravity. If we set pi equals 0, okay. But we introduce pi here. Okay. Then we take the so-called decoupling limit, where mass goes to 0 and Planck scale goes to infinity with this combination fixed. Okay, and then we can decouple the interaction between h mu nu and pi. Okay, especially the vector part and the tensor part of h mu nu are decoupled from the scalar part of this part. This one. Okay. So let's consider the scalar part of pi a. So we consider pi a downstairs to be derivative of pi. And this is sufficient for analysis of would-be BD ghost, because as we have learned, BD ghost is just 1 degree of freedom, and 1 degree of freedom is just a scalar. Okay, so we want to learn what how BD ghost appears and disappears. Okay, in the new theory. Okay, so we introduce scalar degree of freedom in this way, okay. And then so by expanding pi mu nu with respect to pi, so h mu nu with respect to pi, we get this. Okay, it's very easy. So h mu nu is said to be 0, and pi a downstairs is derivative of pi. Then plugging them to here, then we get this. Okay. So basically, we set g mu nu to be eta mu nu, and then we plug this with this answers here. Then we get the expression for capital H mu nu. Okay, and in the theory proposed by Pierre and Pauli, we have a trace of square and a square trace with a -1. Okay, here. And in this case, by plugging this expression to here, we can see that this is this combination, particular combination, is total derivative. Okay, so this does not contribute to the equation motion for pi. Okay, so there is no ghost in the scalar sector. Okay. This is the reason why Pierce-Pauli theory does not have a ghost. Okay, if we change this coefficient from -1 to something else, then we don't have a total derivative, but something non-trivial. then we end up with a ghost. We can do the same thing in higher order. At the third order, we have 3 combinations. Okay, so the trace of square cubic of h, and h times trace of square, and the cubic of trace. Okay, then let's consider these coefficients as arbitrary constants, and then plug this expression. If we fine tune these coefficients, then this combination turned out to be total derivative. And we have only one free parameter. Okay, if we consider C1 to be free parameter, C2 and C3 are completely determined by the condition that this combination is total derivative. Okay, we can do the same thing at the 4th order and 5th order and up to any order, actually. And actually, at the 4th order, we have additional arbitrary constant. And at the 5th order, we don't have any additional constant. So we have a coefficient of this one, which is gravitational mass squared. And we have one constant from here and one constant from here. In total, we have 4 constants. Okay. In this way, these people found the theory that evade this Broglie-Desargues ghost. Okay. So in a sense, they find a way to avoid Broglie-Desargues ghost by infinite number of fine tunings. Okay. So at each order, we can fine tune the coefficients to get the theory without the ghost. Okay. But this is at this moment, we know that this is free from Broglie-Desargues ghost in the so-called decoupling limit, which is this limit. Okay. But at least this is good. And actually, it turned out that this theory doesn't have a Broglie-Desargues ghost at free nonlinear order away from this decoupling limit. Okay. So this theory is the first example of fully nonlinear massive gravity without Broglie-Desargues ghost since 1972. Okay. So after almost about 40 years, they found the theory to avoid Broglie-Desargues ghost. And this is purely classical, but said to be technically natural. Because if we consider this fine-tuned potential, then we can compute the loop corrections. And as far as gravitational mass is small, then corrections are shown to be small. Okay. And then these properties of 5-degree freedom depends on the background. At least around the flat background, at the fully nonlinear level, we have a nice theory. But if we change the theory background within the same theory, we need to check the property of the theory. Okay. For example, cosmological background. Okay. But anyway, so this theory is described by, of course, metric and 4 scalar fields that was introduced in this way. Okay. And this theory has not only the 4D diffeomorphism invariance, because we recovered it by introducing 4 scalars, but also Poincaré symmetry in the field space. So we can consider a shift of phi a, considering them as if they are kind of coordinates, but they are coordinates in the field space. So we can consider shift of 4 coordinates. Ca are constants, and also we can consider Lorentz transformation in the field space. Okay. Still, the theory is invariant. So this means that everything should be written in terms of kind of Minkowski metric. So if we demand this symmetry, as we have learned from the classes of special relativity, everything should be written in terms of Minkowski metric. Okay. So this is Minkowski metric, and from this Minkowski metric, we can define the pullback to the space-time in this way. Okay. So this is sometimes called the fiduciary metric. Okay. So we have the original metric G mu nu, which is usually called physical metric, but also we have additional metric, which is sometimes called fiduciary metric. in terms of G mu nu and F mu nu, the action of this theory can be written in a nice way. So this theory was originally constructed by infinite number of fine tunings. So this theory is well defined, but it's not so convenient. Okay, we have to do infinite number of fine tuning and compute all coefficients up to arbitrary order. But somehow these people found a way to resum, okay, these infinite number of terms in a compact form. Okay, this is the result of the resummation. Okay, so we have gravitational mass here, and also we have two additional constants. Okay, as I said, here we have gravitational mass squared in front of here, and we have additional constant here. From the fourth order, we have additional constant. From fifth order, we don't have any additional arbitrary constant. Okay. So we have three constants: gravitational mass and alpha 3 and alpha 4. In terms of them, action is written this way. Of course, we have Einstein-Hewitt action plus this term. Okay. And L2, L3, and L4 are written in terms of F mu nu through this combination. Okay. This Curie K mu nu is Kronecker delta minus square root of this combination. This is G mu nu upstairs, and this F mu nu downstairs. Then we have matrix. We compute the square root in the sense of matrix. Then take the difference between this one, this. This defines K mu nu. And then the L2, L3, and L4 are defined in this way. Okay. So this square bracket represents trace. So this is the square of trace, and this is the trace of square. So this is very similar to Fierce-Pauli gravitational mass term. And then the L3 and L4 are defined in this way, but at the third order and the fourth order in K mu nu, okay, with a specific coefficient. Then the so by plugging this, okay, so yes, indeed, if we consider decoupling limit and plugging this to here, then the K mu nu turned out to be just the second derivative of pi. Then plugging this to here or here or here, we can show that they are total derivative. Okay, so indeed they are so BD ghosts do not appear, at least in the decoupling limit. Okay, so it's good. So in a sense, by demanding this necessary condition, namely the absence of BD ghost in the decoupling limit, this is a necessary condition for the absence of BD ghost in any regime. So by requiring this necessary condition, they found a unique theory, okay, up to 3 constants. Okay. And it's not clear at this point whether this is sufficient or not, but it turns out that indeed this is sufficient. So these people show that there's no BD ghost away from decoupling limit. Okay. So let me sketch the proof of this absence of Borgia-Delta ghost. It's a bit long, so that I will not explain in detail, but this is just a sketch. Okay. So if we compute the Hamiltonian of this theory by doing ADM decomposition as this 3+1 decomposition, lapse and shift and the 3D metric, then we can compute the Hamiltonian, and then the Hamiltonian is still nonlinear in N and Ni. And if we go back here, then if the Hamiltonian is nonlinear in lapse and shift, then indeed this secondary constraints includes lapse and shift. So you might think that these secondary constraints can be solved with respect to lapse and shift because they show up here and here. Okay, so we have some worries. So this may suggest that there may be BD ghost still. But real question is this one. So does it remain nonlinear in N after eliminating Ni? Okay. So we just need one additional secondary constraint, hoping that there are one more condition from the kind of tertiary constraint. So at least we want to have a one constraint from this kind of condition. Okay. So after solving this, plugging this to here, if the constraint turned out to be independent of laps, that's okay. Okay. If not, I mean, so that this answer to this question is yes, then there's a BD ghost. Okay. If the answer to this question is no, there's no BD ghost. Okay. And the trick that Hassan and Rosen took in order to show that answer to this question is no is just field redefinition. This is a very smart change of variable. Okay. So this is the original shift vector. And they introduced the nonlinear function. I mean, so C0 and Ci nonlinear function of new vector Nj, Ni or Nj. And assume that original shift vector is linear in laps when written in terms of new vector small ni. Then they chose these nonlinear functions so that the Hamiltonian has a specific form. Okay, and in this way, if we choose this coefficient in a clever way, then after solving the equation, so after eliminating small n, then the Hamiltonian is explicitly linear n. Actually, it turned out that Hamiltonian is linear in laps already before solving with respect to small i, small n, small ni. So that if we choose these coefficients in a clever way, okay. This is equivalent to saying that the answer to this question is no. Okay. So after solving the constraint with respect to shift, either capital N or small n, the Hamiltonian is linear in n, laps function. Okay. So the constraints after solving shift vectors, either small n or large n, like this. So we have a constraint coming from coefficient of laps function. Okay, so if we compute the pi n dot, we just need to compute the Poisson bracket between this one and this one. Then we get the coefficient of n. So we have contribution from here, and we have contribution from here, and also contribution from here. So we have this kind of constraint. This is independent of laps. Okay, this is good. And then we should demand that the time derivative is also 0. Time derivative of this combination is 0. Then we have a tertiary constraint. Okay. Then we can compute the Poisson brackets of between these two constraints. Then it turned out to be non-zero. So the determinant of this matrix is non-zero, meaning that there is no additional constraints and they are second class. Okay. So here we already eliminated the shift vector by solving the constraints. So we have just 14 components in 14 variables in the phase space. We have laps and its conjugate momenta and 3D metric and their 3D metric and conjugate momenta. Okay. So 14 variables. And we have so we have one first class constraint because all constraints, they do not depend on laps. So the pi n commute with them. So that this is first class. So that this remove 2 phase space dimension. As we have learned yesterday, first class constraint remove 2 degree freedom in phase space. And we have 2 second-class constraints, so we should remove 2. So we end up with 10 phase space dimension, which corresponds to 5 local degree freedom. So this theory does not have Borel data ghost. This agrees with the number of degree freedom in the linear theory. Okay. So finally, we found that so the theory without Borel data ghost was found after almost 40 years. And the answer to this question, we know that the answer is yes. So we can have a graviton mass in a theoretically consistent way. Then it's time to talk about this question. Can we have acceleration without dark energy from graviton mass? And there are some debate about a consistency of this theory based on a so-called positivity bound. But in this talk, in this lecture, I'm not going to go into details about this. Okay, so if you are interested in, please have a look at this paper and this paper. Okay. And so I'd like to consider cosmology from now on. But if you have any questions about the theory part, please have please raise your hand. If not, let me go on. Okay. You have a question?
Please.
I cannot hear you.
You can ask your question. You have to unmute yourself.
Can you hear me?
Yes. Yes.
Yeah, hello. Thank you for the lecture. I have 2 questions actually. The first one, what about the problem of cosmological perturbations that does not give finite quantities in massive gravity? Because I remarked that there was a lot of people who left the field. And the second question, what about also the validity of the theory against the constraint coming from GW 1708-17?
Yes, right. So about cosmology, that will be discussed from now on. So I'm not going to answer now because I don't want to spoil my lectures. And about constraint on the graviton mass from gravitational waves, so there's upper bound, something like a 10 to minus 22 electron volt or something like that. And so yes, as far as graviton mass is smaller than that, that's okay. Yes. And if you want to have acceleration from graviton mass should be much smaller. So acceleration from graviton mass is consistent with observation gravitational waves. Okay, so let me go on to answer your question. Okay, so I'd like to think about the cosmology. And so after this breakthrough, of course, people started to think about cosmology, okay, to answer this question. Okay. So but these people, including these 3 people who found the theory, found a kind of no-go result. Okay, so they said no. We cannot find expanding universe if we demand the homogeneous and isotropic universe. Okay, so they consider the flat Friedmann-Lemaitre-Robertson-Walker ansatz in the unitary gauge, where phi a is said to be xa. Then f mu nu is just eta mu nu. Then the metric is assumed to be flat Friedmann. And then we can compute the equation motion for the metric. And we also want to compute the equation motion for phi, but the phi is said to be already xa. And it's not easy to compute the equation motion for phi a directly, but there's a trick using the kind of Bianchi identity. Okay, so a Bianchi identity means that so this is the so divergence of the equation motion for G mu nu. This is identically equal to this combination. So this is the result of the diffeomorphism invariance, okay, because we introduced the strict-level fields. And then the right-hand side is basically equation motion for phi a. Okay, so instead of computing the right-hand side, we can compute the left-hand side. Okay, so that as far as we know the equation motion for G mu nu, we can just compute the divergence, set the divergence to be 0. We can compute the equation motion for phi. And if we do that for this ansatz in this theory, then this tells us that A dot equals 0. A is a scale factor, size of the universe. So the universe cannot expand, at least in this ansatz. And so if this applies to all Friedman universe, then the universe cannot expand. Okay. So this is a situation. This was the situation at the beginning. Okay. Actually, at this point, I got interested in this theory and started to think about massive gravity in the context of cosmology. So it was, in a sense, bad timing, but actually it was a good timing because we were able to improve this situation. Okay. So as you can imagine from the fact that I put the seesaw here, this situation changes from time to time. Okay, since 2011. Okay. So fortunately, we found another solution. Okay, so previously they considered flat Friedman background, but we can consider another type of Friedman universe. So we consider the open Friedman universe for the following reason. Okay, so if mu nu, which is a fiducial metric, spontaneously breaks diffeo, because this is a kind of fixed metric, and in order to find the homogeneous isotropic universe, we should respect the symmetry, namely the homogeneity and isotropy, by both G mu nu and F mu nu. So the F mu nu should be of the Friedman universe, FLRW form, of course. And but F mu nu is just a pullback of Minkowski metric to the spacetime, as we have learned. And in other words, we need Friedman coordinates, FLRW coordinates of Minkowski metric. Okay. The question is, can we foliate the Minkowski metric in such a way that the metric looks like a special case of FLRW? Okay. We know that there is no closed FLRW chart for Minkowski metric. It's very easy. We know Friedman equation. And the left-hand side, we have h squared and the curvature term. And so on the other hand, the right-hand side, we have energy density and Minkowski metric or curvature. Minkowski metric has a 0 curvature, so the right-hand side is 0. And the left-hand side is h squared plus curvature. So if curvature is positive, then there is no way to satisfy this equation, Friedman equation, with vacuum situation. Okay, so there is no way to foliate a Minkowski metric by closed FLRW chart. So we cannot give ansatz. So without doing any computation, we know that this theory does not have a closed FLRW universe solution. But we can find open Friedman Lemaitre-Robertson-Walker ansatz. So basically this is the so-called mirror universe. So knowing that the Minkowski metric can be written in the form of mirror universe, we can consider this kind of ansatz, plugging this to the definition of F mu nu, which is defined, here. We can show that the F mu nu is of this form. Okay, and this is hyperboloid. Okay, so this is open universe. And we can consider open universe ansatz for the physical metric G mu nu, then plug them to the equation motion of the massive gravity. This theory. Sometimes, often this theory is called the DRGT, okay? Because of the names of the people who found this theory, DRGT. Okay? So by plugging them to equation motion of the DRGT theory, we can find a solution. Okay. equation motion for phi A turned out to be this kind of equation. Okay, so we have two factors. One is this one, and the other one is this. Okay, if we set k equals 0, then there is no way to satisfy this equation. Okay, because so let's consider first solution. Okay, this one. And this means that A dot is given by this. And if we plug this to here, actually, it turns out that this is also flat metric, flat Minkowski. Not flat, I mean, the Minkowski metric in the open chart, namely the middle universe, empty universe. Okay, so we cannot live there. Our universe is expanding in a non-trivial way. Okay, so G min is just Minkowski. So we shouldn't choose this one. Okay, and so let's consider other solution. This means that this combination satisfies second order algebraic equation. So we can solve this. Okay, then the f is given by this, where x is a solution to this algebraic equation. So given by this. Okay, and the latter solution, this solution does not exist if k is set to be 0 from the beginning. Okay, if k is 0, then f is 0. F is infinite. Or if we specify f from the beginning, then the x turned out to be 0. So we cannot do that. Sorry, x is given by this. So a turned out to be 0. Sorry, scale factor is 0. So we cannot find a solution if k is 0. Okay, this is the reason why we cannot find the flat FLRW solution. But the open universe is okay. And so by then we can consider the metric equation motion. Then it turned out that equation motion give us this kind of equation, which is a modified Friedman equation. Left-hand side is the same. This is the same as Friedman equation, but we have additional term given by gravitational mass. So this is proportional to gravitational mass square. Okay. And this is positive if the two additional parameters, alpha 3 and alpha 4, are in this regime or in this regime. Okay. Here, this is plus branch and minus branch corresponding to the sign of this part. Okay, because we have a second order algebraic equation, we have two solutions, plus branch and minus branch. Anyway, if we are here or here, then we can have acceleration without dark energy from Brighton mass. So we were very happy. And also we found that if we slightly extend the theory, then we can extend this kind of solution to not only flat FLRW, but also closed and open, not only open FLRW, but also closed and flat universe. Okay, so we had some nice results. But then after that, we started to think about the cosmological perturbation. Okay, then the cosmological perturbation showed some strange behavior. So we had gravitational waves, and it had a mass as expected, but the scalar perturbation and the vector perturbation did not show up at the linear order. So we decided to perform some nonlinear analysis. Okay, and then we found a kind of instability, new instability at the nonlinear level. At the linear order, it doesn't show up, but at the nonlinear order, it shows up. And this is within 5 degrees of freedom of massive gravity. So this is not Borel-Desargues ghost. And this is not another ghost, which is known as Higuchi ghost, because Higuchi ghost appears in the linear level. This shows up only at the nonlinear level. So in a sense, we were kind of happy because we found a new phenomena in massive gravity. But of course, we are very unhappy because kind of sad, because we killed our own solutions. A kind of mixed feeling. And so then we tried to find a way out. One possibility is to find a new class of solutions in the so the same theory. So we found the kind of anisotropic solution. So if we assume homogeneity and isotropy, then all solutions are unstable in a sense, one way or another. That's what we found. So we need to break either homogeneity and isotropy. We decided to break the latter. Then we found the anisotropic solution. But in this solution, what is interesting is that our metric G mu nu is homogeneous and isotropic. Then another solution, another F mu nu, another metric, physical metric, F mu nu is also homogeneous and isotropic. But if we put them together, the whole system is not isotropic. In other words, the Killing vector for rotation for G mu nu and Killing vector for F mu nu for rotation do not agree. So in this sense, the whole system is anisotropic, but our metric is isotropic and also homogeneous. So this may be one possibility. And another possibility is to consider to develop new theory. Okay. So the one possibility is the so-called what we call the minimal theory of massive gravity. This is minimal in the sense that we have only 2 degrees of freedom. Okay. So massive gravity usually have 5 degrees of freedom, but we found a theory with just 2 degrees of freedom. That corresponds to massive gravitational waves. And because we don't have a scalar and vector degree of freedom, this theory is completely stable. And what is nice is that we can accommodate exactly the same FLRW background as in DRGT, so that we can have acceleration without dark energy. So gravitational mass can accelerate the universe. And as I said, there is no instability, so no BD ghost, no Higuchi ghost, no nonlinear ghost that we have found. And also the positivity bound that I have mentioned very briefly does not apply to this theory. I think I don't have time to explain how to obtain this theory, but let me briefly mention some phenomenologies. Okay, so we can have self-acceleration without dark energy if we are in this regime or in this regime. Alpha 3 and alpha 4 are dimensionless constants in parameters in this theory. Okay. And so we have 2 branches of solutions actually. So let's go back here. And the equation motion for the background is the same, so that we have this kind of equation. And the solution that have acceleration without dark energy is obtained by setting this to be 0. But if we set this to be 0, we have another branch of solution. If we consider more general fiducial metric. If we consider Minkowski fiducial metric, then this turns out to be Minkowski, so that we cannot live there. But if we consider more general fiducial metric, like Dojiter, or more general one, Friedman, for example, sorry. Yes. Then we can find another solution. Then the gravity is modified. So scalar and the vector perturbation are modified. And so we can try to fit the data. Indeed, this theory can fit some data better than the standard model of cosmology, lambda CDM. Oh, sorry, this is not lambda DCDM, lambda CDM, sorry. Okay. So this is, I think, lambda CDM is this red dotted line. And this minimal theory massive gravity with some parameter fits the data slightly better. And we have 2 minima of a maximum of likelihood. So we have two possibilities to fit the data better than lambda CDM. Okay. And we can also find the black hole and the stars, at least for spherical symmetry case. And we have found that any solution of a general relativity that can render spatially flat by a coordinate change is also a solution of this self-accelerating branch of minimal theory massive gravity, with or without matter. So for example, Schwarzschild solution is a solution, and so we can have black hole, and also this solution can be an exterior solution of a star, and also we can consider gravitational collapse, and also interior solution of a star. And what is nice about this solution is that there is no strong coupling. In massive gravity, there are some many spherical symmetric solutions, and many of them suffer from the strong coupling. But this solution does not suffer from strong coupling. And also, there are no additional singularities except for that already exist in general relativity. Okay. Also, in cosmology, this theory has an interesting implication. So suppose that the coefficient in front of graviton mass is a function of some scalar field. So the graviton mass changes from large value to small value. Small value means that smaller than the upper bound implied by observation gravitational waves. But in the early universe, graviton mass can be large. And for example, during inflation, if graviton mass is large, then the massive graviton is excited. And then after inflation, for a while, graviton mass can be large. Then the energy density of graviton mass, energy density of graviton can decay as matter. Massive field scale, energy density of massive field scale like 1 over a cube. As energy density is basically the product of mass and number of particles, and the number density of particles, and number density of particles decays as 1 over volume. So the decay is like a 1 over a cube. And then so energy density of massive graviton, which represents gravitational waves, can decay like 1 over a cube for a while. And then after a while, graviton mass goes down to small value, then they start decaying as a 1 over a to 4. Okay, as in the standard case, okay, like a general relativity. Okay, so because a massless field has each graviton has energy of frequency of order of frequency, and the frequency also redshift as the universe expands. So the energy density of massless field decays faster than massive field. Okay, and but up to some point, energy density of graviton, massive graviton decays slower. So for this reason, graviton, so energy density of gravitational waves can be enhanced compared to general relativity. So then putting the constraint from the CMB, still we can have a large enough, this is too large, but we can have some case, we can have a large enough amplitude of gravitational waves at the observable range of frequencies. Okay. So the massive gravity of this type may have some interesting implications. Okay. So this is another possibility to evade this problem. Okay. And also another possibility is to have two metrics, dynamical one, instead of, okay, I have a question. Okay. Why do you fix the high frequency cut? Yes, here, yes. This is because of the end of the inflation, yes. At some point, inflation ends and gravitons are not produced. Yes. So there is a cutoff at the high frequency. Okay, so then I hope this answers your question. If not, please ask later. Okay. And then we can consider extension of massive gravity by promoting the fiduciary metric F mu nu to dynamical one. So we have two metrics, and in the standard case, extension of DRGT theory, we have 7 degrees of freedom. And again, we have some, we tend to have problems because of extra degree of freedom. So recently, with Antonio and Francois and Michele, we found a very nice theory with just 4 degrees of freedom. Okay, we have 2 metrics, and one metric corresponds to massive gravitational waves. The other one corresponds to massless gravitational waves. Okay, and then we have no instabilities like a BD ghost and Higuchi ghost, no strong coupling, and background freedom FLRW backgrounds are exactly the same as the so-called Hassan-Rosen bigravity, which is an extension of DRGT to bigravity setup. So we have a solution that accelerates the universe without the dark energy, and also there's another solution. Okay. Yes. And then the construction steps are basically the same as minimal theory master gravity, but I don't have time to explain this. And but anyway, this is a very fast example of a completely stable and cosmologically viable theory of nonlinear bigravity. And this provides a testing ground for gravitational phenomena, such as gravitational oscillation, and they can be probed by gravitational waves. Okay, gravitational oscillation is the oscillation between massive graviton and massless gravitons. Okay, so actually the massless graviton is actually a linear combination of perturbation of G mu nu and the perturbation of F mu nu, and the massive graviton is also a linear combination, not the G mu nu itself, or not the perturbation of G mu nu itself, or perturbation of F mu nu itself. Their combinations are massless and massive gravitons. Okay. This means that the matter couples to linear combination of massive graviton and massless graviton. So if we have some gravitational wave source, such as binary neutron stars, then not only massless gravitons, but also massive gravitons are produced. Okay, and then as I said, G mu nu and F mu nu are not massless state or massive state. So indeed they oscillate as they propagate. Then we detect only perturbation of G mu nu. So this kind of phenomena may be probed by observation, and this theory provides interesting testing ground. Okay. So also graviton mass, massive graviton may be the source of dark matter in some cases, and because whenever massless gravitons are produced, the massive gravitons are also produced. Okay, and massive gravitons are massive, and if they are stable enough, then there can be a part of or all of dark matter. Okay. And this paper was written before the discovery of this theory, and so we had to impose some conditions like absence of Higuchi ghost and so on during inflation, but we are free from those constraints. So I think this kind of idea can be applied to this new theory and find a new regime of parameters. This is a prop from this paper, and so in some cases we can find a connection between the mass of dark matter and amplitude of gravitational waves, because whenever gravitational waves are produced, dark matter are also produced. Okay. So we can do something similar for the new theory probably. Okay. So anyway, so this new theory of minimal theory by gravity, it can be considered a solution to this problem. Okay. So let me summarize the massive gravity part. So we now have nonlinear massive gravity found by DRGT in 2010. This is free from Borrellia-Desargues ghost, and if we consider FLRW background, there's no closed Friedman solution and also flat background, but we can find open solution, okay, with acceleration without the dark energy. Okay. And if we slightly extend the theory to consider, say, Friedman type or Dojita type fiduciary metric, then we can accommodate all types of FLRW universe. But unfortunately, these solutions are strongly coupled and there are ghost instability. Okay. So in order to find a stable cosmology in the context of massive gravity, we need to either consider new class of cosmological solutions in this context by breaking either homogeneity or isotropy, or we need to consider extended theories. Okay. So two possibilities that I discussed, minimal theory of massive gravity and minimal theory by gravity. They provide nonlinear completion of a DRGT type stable accelerating cosmology. Okay. So before moving to going to the next section, if you have a question, please ask. Yes, please.
Yeah, so do you hear me?
Yes.
Yes.
Yeah, so it's about the motivation behind the minimal theory of massive gravity. I was wondering if even gravitational wave constraint doesn't put higher constraint comparing to acceleration for the massive graviton. But so you consider that massive gravity, or even by gravity, is not valid for cosmology. This is your conclusion, and we need really.
Right. Yes.
Okay.
Yes. So
because you didn't talk about by gravity, you talk only about massive gravity. So I was wondering if the same case, for example, for by gravity, for its viability for cosmology.
Right. So in the case of massive gravity, we have instability always if we consider homogeneous isotropic background. So that we need to avoid those instabilities. The simplest way to avoid those instabilities get rid of those degree freedom. That's the minimal theory of massive gravity. So we exclude any type of instability by considering theory with 2 degree freedom. And we can consider by gravity. We can consider by gravity.
Excuse me, before going to how you get rid of this degrees of freedom, you put more constraints, or how you do that?
Yes. Yeah, basically yes. Yeah, this is the 3 steps. So so let me briefly explain. Okay, so yeah, so the first we start with the DRGT theory and write down the theory in terms of the Vierbein. Vierbein is a kind of square root of a metric. So we introduce a Vierbein for G mu nu and a Vierbein for F mu nu, and write down the theory in terms of those Vierbeins. Okay, and originally we had a symmetry. I mean, we can consider boost of local frame in this way, so that we have local Lorentz transformation for G mu nu and the local Lorentz transformation for F mu nu. And if we do the same transformation, this is a symmetry of DRGT theory in the Vierbein formulation. And also, if we take the variation with respect to them, and then we get the equation motion. And if we satisfy them, then we go back to DRGT. But if we fix the local Lorentz frame by hand, then this is not allowed in the DRGT, but we have a new theory. And we chose a specific frame that is called ADM Vierbein. These are the very nice properties. And if we plug this ADM Vierbein to DRGT, then we have a theory with 3 degree freedom, not 5. So by just choosing the Lorentz frame in a nice way, we can remove 2 out of 5. So we end up with 3 degree freedom. But we still have 1 additional. So that we removed the 1 additional degree freedom by adding 2 additional constraints. Okay, in a very careful way. If we do this step in a careless way, then we end up with a theory without nice cosmology. Okay, we chose these two constraints in a very careful way. Then we end up with minimal theory of mass gravity. The construction of minimal theory of bigravity is also similar. Yes. But we have 4-degree freedom. Okay, so this is answer to your first question. And I think you asked about bigravity. And in bigravity cosmology, and we can find a stable solution. But in that case, we need to have a large gravitational mass. And so if the gravitational mass is, I mean, if we send the gravitational mass to be very, very large, then of course the massive graviton is not excited. So we go back to general relativity. That's not interesting. Okay. And also even if we consider some nice value of gravitational mass in such a way that cosmology or perturbation or some phenomenology changes, but still instability can be avoided. But still, we cannot apply bigravity to the early universe because there is a strong coupling scale, which is relatively low if gravitational mass is not extremely high. Okay, so we cannot apply the theory to high in the early universe. So it would be nice to have a bigravity without any instabilities or strong coupling, and this is the reason why we try to find a minimal theory of bigravity, and we recently found it. Actually, we tried to find this theory soon after we found this theory. So with Antonio, and then we couldn't find for a long time. But then recently Francois and Mickey joined, and then somehow we found finally.
And you talk also about the black hole solution. So there is only a solution of GR. We didn't find new solutions even here in black holes in this kind of theories.
I think yeah. So in this theory, we have 2 branches. Other branch have a new solution, I think.
Okay.
And this also even in this branch, if we have a rotating black hole, we should have a deviation from GR.
Okay.
And in this theory, we don't know. I think we have, again, probably we have 2 branches, and self-rotating branch may be similar to GR, but other branch may have some deviation. Rotating black hole, I don't know. I have no idea. Yes.
Okay, thank you very much.
Welcome.
Shinji, there is a question from Guillaume, who asks whether there are developments of massive gravity in higher dimensions, and if yes, are they similar to the 4-dimensional case?
Yes, similar. Yes. So if we want to follow the RGT setup, similar to the RGT setup, and let me go back here. So if we go to the higher dimension, we have more terms. I mean, in the case of Lovelock, we have learned that the number of terms increase as we increase number of dimensions. Also, the RGT, if we increase the number of dimensions, we have more combinations. That is total derivative if we substitute this to combination, right? And then as we go to the higher dimension, we have more terms. And then if we compactify extra dimensions, we have a kind of massive gravity with the extra scalars and the vectors and so on. Yes, and that can be considered. And I think there are some papers. Yes, yep. So in a specific case, and dropping vector and concentrating only one scalar, this may be similar to the so-called quasi-dilaton gravity, quasi-dilaton, which is similar to dilaton gravity, but in the context of massive gravity. And but still, even with extra scalars and vectors, it's not easy to find a stable cosmological solutions. Yeah.
Okay, thank you.
Welcome.
I don't see other questions.
Okay.
There is someone. Yes.
Hi. So about these 2 branches, is there any way of, let's say, observe something that allows you to say, I'm going to choose this specific branch?
Yes, of course, yes. That's a very nice question. Good question. And we have 2 branches. And for example, in the case of minimal theory of massive gravity, in the self-accelerating branch, the scalar perturbation and vector perturbation follows exactly the same equations as in general relativity. So the background is the same as lambda CDM, and the perturbation also the same as lambda CDM. So the phenomenon, so here, for example, here I wrote lambda CDM, but this is actually the same as the self-accelerating branch of minimal theory of mass gravity. And on the other hand, in the other branch, which we call the normal branch, have a modification to scalar and vector perturbation. So the yes. So this is a normal branch. So that, as you see, there are some difference. Okay. So in principle, we can distinguish these two branches. Yes. By looking at the perturbation.
Okay, thank you.
You're welcome. Also, I expect a similar thing for minimal theory of bigravity. Yes. If there are no other questions, may I go on to the next section?
Yeah, I don't see any other questions, so you can go on.
Okay, so let's move on to section 6, which is about Hojava-Lifshitz gravity. Okay, so this is a kind of a candidate for quantum gravity, and recently this theory was proved to be denormalizable, and there's no ghost associated with higher derivative terms, so the probability is unitary. So this is a good candidate for quantum gravity. Of course, the string theory is a leading candidate for quantum gravity, but this is also another kind of candidate. Okay. So let me start with power counting argument. So that in order to explain that this theory is power counting denormalizable. Okay. So I think I don't have time to show, to explain how denormalizability was proved. But at least I can explain how this theory was constructed so that people expected the denormalizability. Okay, so the power counting denormalizability is easy to impose, and it is an indication of denormalizability. Okay, so for this reason, I'd like to explain what power counting denormalizability means. Okay, and for this purpose, I need to explain power counting. Okay, this I think this is similar to what we have done in the context of effective field theory of scalar tensor theory. So maybe you can understand very easily. So let's consider scalar field for simplicity with the time kinetic term of this form, phi dot square, as usual. And then let's consider scaling of time coordinate. We just multiply time coordinate by some factor b, and spatial coordinate by the same factor b. Okay, and then we consider phi to be scaled like this, where s is a number to be determined from now. Okay, s is not yet fixed, but we are going to fix s so that this part of the action is invariant under the scaling. Okay, and of course, energy goes like energy is the inverse of time, so that we have B inverse here. Okay, now from dt we have one factor of B and 3 from the volume. From 2 time derivative we have -2, and we have 2s from 2 phi's. So they must sum up to 0 in order to make this to be invariant under this scaling. Okay, then the s turned out to be -1. Okay, this means that the scalar field scales like energy, as we know. Okay, mass dimension of scalar field is 1, and so as we change the energy scale, the amplitude of quantum fluctuation phi scales like energy. At high energy, amplitude becomes large. At low energy, it becomes small. Okay, and let's try to estimate the amplitude of this kind of interaction. Okay, phi to n. Okay, then when we change energy, how this interaction scale. Okay, so let's think about this. And as a function of energy, this is scale like this. Okay, this -1 comes from this -1. 1 comes from dt, 3 comes from volume, and s comes from n5. Okay, and we know that s is -1, so this exponent, including minus, is non-positive if n is smaller than or equal to 4. So if this condition is satisfied, then as we increase energy, this interaction does not blow up. So we have a good control at high energy. So this is a condition for renormalizability in the sense of power counting. So this is a power counting renormalizability. Very easy to understand. Okay. Unfortunately, gravity is highly nonlinear, and therefore there are interactions with n larger than 4, and so the gravity is usually thought to be non-renormalizable in field theory. Okay. Of course, in string theory, we don't consider field theory because string is I mean the usual. We don't consider usual string field theory because the string is an extended object. But if you consider field theory, then usually we consider that the gravity is non-renormalizable because of this. Okay. The idea by Hojawa is very simple, but kind of dangerous. Okay, so we introduce so-called anisotropic scaling at the fundamental level. Okay, so we consider scaling of time and scaling of x in different ways. Okay, spatial coordinate is multiplied by b, but time coordinate is multiplied by b to z. Okay, z is a number which is fixed by the theory. Okay, so the value of z is a kind of part of the definition of the theory. So once we fix the theory, we know b. Okay, and so energy is scaled b to minus z. Okay, and then again we want to determine s so that this is invariant under scaling. Okay, from dt we have z because z is here. From volume we have 3, and from two time derivatives we have minus 2z, and from 2 phi's we have 2s. They must sum up to 0. Okay, and then the s is said to be this value. Of course, if z equals 1, s is -1, we go back to this scaling. Okay. By the way, the reason so that we have a question. Okay, what is the motivation for this scaling? Okay, so this scaling be not the scaling but the scaling, meaning that the reason why we want, I think he or she is asking why we want to change scaling from this one to this one. Okay. The reason is that if we keep this scaling, it's really difficult to have a renormalized theory. Okay. And but if we consider this kind of scaling, then it's easy to find a theory with power counting renormalizability, and can be a candidate for quantum gravity. That's the reason. And the price to pay is to break Lorentz invariance at the level of the theory, not spontaneous, fundamental. Okay. And we need to recover Lorentz invariance at low energy by hopefully by RG flow. Okay, so that is the motivation. The motivation is to find the quantum gravity. Anyway, so by changing the scaling, then we have a different formula. If we set z equal 1, we go back to the previous formula. But what is interesting is that if z equals 3, then s is 0. So if z equals 3, the phi does not scale. In other words, as we change energy scale, the amplitude of quantum fluctuation of phi does not change. So let's estimate the importance of this kind of operator again. So again, we have this time we have minus z instead of -1 from this minus z, and z from dt, and 3 from volume. Okay, because x scales like b, so we have 3 here. and ns from n5. Okay, and then we want to make this to be non-positive. Oh, by the way, considering the fact that I don't see reply from the him, I guess he is not. He was asking something else. Probably he was asking how to get this kind of scaling. I'll answer this question later. So when we consider action, we'll see naturally. Yes. So there's a way to realize this scaling naturally. Yes. And then anyway, so for z equals 3, s equals 0, and by plugging z equals 3 and s equals 0, this is always negative. Okay. So as we go to high n, still this is negative. So the high energy behavior is well controlled. So any nonlinear interactions are renormalizable. This is the idea. So if gravity behaves like this, then we have a theory with power counting renormalizability. Okay, and this may be a candidate for quantum gravity. Okay. Now, Hodge-Blasius gravity is a theory of gravity that realizes z equals 3 scaling at UV. UV means high energy and high momentum and long, short time scale, short distance. And therefore, this is a power counting renormalizable. And without z equals 3 scaling, it's really difficult to get a renormalizable theory. We can consider, as I mentioned yesterday briefly, we can consider curvature square term without invoking z equals 3, just z equals 1, a Lorentz invariant case. But if we have R square term, R square and R mu nu square and R mu nu rho sigma square, then we end up with ghost. Okay. So without the ghost, but power counting renormalizability, we need to break this isotropy with respect to time and space. And z equals 3 is a good number. Okay. Anyway, so the renormalizability was recently proved, not recently, 2016. This was proved in any number of space-time dimensions. But if we go to higher dimensions, suppose that the number of space dimension is small d, then we need to consider z equals small d. Say in 5 space-time dimensions, z should be 4. Okay. And there's no so-called Ostrogolsky ghost associated with higher time derivatives. Therefore, this theory is likely to be unitary. And people, these actually same kind of people, they analyze the renormalization group flow in 2+1 dimensions, and then the theory was shown to be asymptotically free. And the price to pay is that the Lorentz invariance is broken at UV scale. So we need to recover Lorentz invariance, at least in the matter sector. And also the speed of gravitational waves should be recovered to be 1 at low energy. Okay. So the hope is that there may be Lorentz invariant IR fixed point. Actually, these people long time ago considered a generic setup where Lorentz invariance is not fundamental symmetry, but kind of emergent symmetry. So that they found that Lorentz invariant IR fixed point is generic. Namely, as we consider quantum collections, as we go down to low energy, Lorentz invariance emerges automatically. This is really good. And on the other hand, and also this may apply to gravitational waves as well. But running towards IR is very slow, logarithmic. So that we need to speed up. And well, there are some ideas in the literatures. For example, Shinji may speed up the renormalization group flow towards IR fixed point, or some strong dynamics may help. But this is still under investigation, and we don't know whether this is possible or not. So this is a still open question, but still there is a hope. Anyway, what is nice is that in the UV, theory is renormalizable and probably unitary. So we have a good quantum gravity. Okay. So this is a construction. Okay, so the this is the simplest version, which is called a projectable version. Actually, when Hojawa proposed the theory, he proposed this version. Okay, so we consider 3+1 splitting of the metric, shift lapse and shift and 3D metric, and here the projectability means that the lapse is said to be function of time. I will explain this later a bit more. Okay, then we can construct ADM metric 3+1 decomposition in this way. But this is emergent in the IR. In the UV at high energy, what makes sense is just a combination of lapse and shift and the 3D metric. 4D metric does not make sense in the UV. But in the IR, we can construct this. Okay, and then the fundamental symmetry of this theory is the so-called fluorescence preserving diffeol, which is a combination of change of time to new time and spatial diffeomorphism, which can depend on time. Okay, so on each constant time surface, we can change coordinate arbitrarily, and coordinate change here and define coordinate change on different time slicing can be independent, but we cannot change this slicing. Fluorescence is kept because time goes to function of time. This doesn't depend on x, so the slicing is the same, fluorescence is the same, but on each slice we can change coordinate. Okay, this is a fundamental symmetry, and we want to recover realize anisotropic scaling with z equals 3 in the UV to have a renormalizable theory. Okay, and because of this symmetry, we can use the following ingredients in the action: ndt squared g times volume integral. So this is invariant volume element, and the 3D metric, and covariant derivative associated with 3D metric and 3D curvature. We don't need to consider wild tensor because in 3D wild tensor is vanishing identically. Okay, and we can consider Kij extrinsic curvature instead of Gij dot. Gij dot is needed to construct a kinetic term for Gij, but this is not tensor with respect to 3D, so we need to use this. Okay, then we can find action. Okay, but let me explain a bit about different versions of Hojawa-based gravity. Before that, so original proposal was with projectability condition, namely the lapse is said to be function of time. Okay, and in this version, renormalizability was proved. Okay, if we try to extend this function of time to function of time and space, then it's not consistent if we do it in a naive way. But by including the derivative of lapse function with respect to space, we can define kind of acceleration vector, and we can construct new terms out of this on top of these ingredients. Then we can cure the problem pointed out by these people, and we have a consistent non-projectable extension. Okay. Also, we can have another extension, so-called U1 extension, to get rid of the scalar graviton that I will explain later. Okay. So this is, but this is a bit complicated. So I explain the simplest version, this one. Okay. And projectability version, projectability condition is motivated by the fundamental symmetry, which is a Fluorescence preserving diffeol. So the dt is function of time, dxi is function of t and xi. Okay. And then the Gij and ni and n transform in this way. So if we consider n to be function of time, then you can easily see that delta n, change of lapse, is also function of time. Because, okay, so this indeed, this is 0 if n is a function of time. And this is function of time, this is function of time, this is because f is function of time. Okay, so the delta n is also a function of time. So the n after transformation remains to be function of time. So it's consistent to set n to be function of time. And also the n is gauge degree of freedom associated with space independent timely parameterization. So it's natural to restrict n to be space independent. As a result, Hamiltonian constraint, which is equation motion for n, is an equation integrated over whole space. So the Hamiltonian constraint is basically the variation of the action with respect to lapse. And but the lapse is function of time at the level of the theory. So if we do that, if we take a variation with respect to n of t, function of time, then we have a expression in which integration over space remains. So the Hamiltonian constraint is an integration over whole space. I will discuss more about implication of this later. Okay. Anyway, so we can construct the theory, action of this theory by this fundamental symmetry and the requirement that anisotropic scaling with z equals 3 is realized in the UV. Okay, by using these ingredients. Okay, so let's do that. So first of all, we want to have a kinetic term. So the Kij squared, there are two ways, trace of square and square of trace. So Kij and K squared. The K is a trace of Kij. And this coefficient is arbitrary. In general relativity, we have more symmetry, so the lambda is said to be 1. But in this theory, we have less symmetry. As a result, lambda is arbitrary. And we don't want to have more terms. And also we construct a model Lagrangian, which have only 2 time derivatives. Then if the theory is renormalizable, then the other terms are not generated by quantum correction. So once we fix the Lagrangian, which is renormalizable, then that's it. That's it. We don't have more terms. Other terms are not generated by quantum correction. For this reason, let's keep up to second time derivatives. This avoids the ghost. Okay, and then in order to realize z equals 3 scaling, we need to balance 2 time derivatives by 6 special derivatives. Okay, then we have a z equals 3 scaling. Z equals 3 scaling means that the time should be something like, should scale like a spatial coordinate to 3. Okay, cubic of space should be time. So when we have 2 time derivatives, we should have 6 special derivatives. There are 1, 2, 3, 4, 5, actually 6 combinations, but this one can be written in terms of other terms after doing integration by part. So up to integration by total derivatives, we have just 5 terms for z equals 3. Okay, so at high energy, we have just 7 terms, 2 plus 5, that's all. By putting some coefficient here, we have action in the UV. Then we have a z equals 3 scaling automatically. Okay, this is the reason why we consider z equals 3 scaling. And if we have z equals 3 scaling, we have a power counting renormalizability. And recently, because of that, theory was proved to be renormalizable. But at low energy, we have more terms, and z equals 2 potentials generated by terms with 4 special derivatives. We have 2 terms, and we also have z equals 1 potential, which just the curvature, which is scalar, 3D scalar, which includes two special derivatives and constant. Okay. In the end, we have 7 plus 1, 2, 3, 4, so the 11 terms. That's all. So total action is like this. Okay. So we have overall coefficient and the lambda, and also cosmetic constant, and coefficient in front of the 3D curvature. which control the speed of gravitational waves, and these higher curvature terms. Okay. And in principle, we can consider 3D space, which consists of several connected pieces. And but we should have a common laps, and because we have a kind of Fourier prism in diffio, and the time is kind of fundamental. So we have common laps, and we have set of 3D metrics and also shift vectors. Okay. Sorry. This should be shift. Sorry, there's a typo. Sorry, this is laps, and this is shift and 3D metrics. Okay, and but of course we are interested in only one of them. We are living in one universe. Okay, and then starting with this total action, we can go to low energy or a long distance. We can get IR action. Okay, so in the IR we have just some terms which have a small number of derivatives. So we can keep only terms with 2 derivatives and just constant. Okay. Then we have something similar to general relativity. Okay. But we have some difference. Indeed, we have lambda here. So in GR, lambda is 1. And also there's a difference. This coefficient is not 1. We have some constant. Okay, so the if lambda goes to 1 and this coefficient CG goes to 1, as energy scale goes down, the RG flow brings us to some IR fixed point. If the IR fixed point has these properties, then it seems that we recover GR. Okay, and but so far, renormalization group flow has not yet been investigated except for 2+1 dimension. In 3+1 dimension, we don't know. So this is a hope. But it is likely that at least they may be a IR fixed point. Okay. Considering the genericity of this kind of scenario. This is very generic. But the speed may be slow. So probably we need to speed up the RG flow to be consistent with the phenomenology. Okay. So the structure of Hodge-Lewis gravity equation motion as follows. So as I said, so here the space may consist of several connected pieces, but we are interested in only one of them. So the on top of that, oh sorry, yes. Sorry. Yes, we have this kind of structure. Okay, so the fundamental symmetry is the Fourier prism in diffio, which consists of the 3D spatial diffio plus space independent time parameterization. Okay, so as a result, okay, this does not lead to constraint at each point because this is a global symmetry, and but this leads to constraints at each point. Okay, so we have 3 local constraints. They are actually momentum constraints, and then so momentum constraints are local, so they at each time and each point. But the Hamilton constraint is some expression which is integrated over whole space, including our universe, other universe, everything. Okay, so for our universe, the Hamilton constraint does not tell us anything, nothing. Yeah. But momentum constraints are local, so we can use them. Okay, and anyway, once the initial condition satisfies those constraints, then the dynamical equation automatically preserve those constraints. Okay, so that we don't need to worry about the constraint once initial data satisfy them. Okay, so we can solve dynamical equations provided that constraints are satisfied at initial time. This is a structure. So let's apply this structure to FLRW spacetime for simplicity. So of course, the FLRW spacetime is an approximate distribution of our universe in our patch of the universe inside Hubble horizon. Okay. And so we don't need to think about Hamilton constraint because this is not local. This is global one. But instead, we have a dynamical equation and also the equation motion matter. Okay, if the matter sector is different invariant, okay, or Lorentz invariant at low energy. Okay, and then we have this kind of equation, a standard conservation equation. Rho I is the energy density of each component. Pi is pressure of each component. Okay, and A is the scale factor. A dot is the derivative of A, time derivative of A. And we can also consider dynamical equation like this. This is local, so we should impose this. And then we may worry about the freedom equation, but actually we can get something like freedom equation by integrating once this equation with respect to time. Okay, and from second order differential equation, we get the first order equation, okay, by integration once. But of course, we get the integration constant. C is the integration constant. Okay, because we don't have Hamilton constraint, we cannot fix C. C is arbitrary constant. What is interesting is that this part behaves like a dark matter, 1 over A cubed. So we have something like a dark matter as integration constant built in the theory without introducing dark matter. Okay. And actually, this kind of consideration can be generalized to arbitrary configuration, at least at the low energy. So let's do that. And so this is the IR limit of Hodge-Willis gravity. But I set this speed of gravitational waves to be 1. And but this argument probably doesn't, yeah, it changes. So we need to set this to be 1, okay, for this argument, okay, hoping that there is a higher fixed point, okay. And now, so this looks like a GR if lambda equal 1. So let's assume that the lambda equal 1 is fixed point, and then the lambda is also 1 at low energy, and CG is 1, and then the equation motion is like, so there are global Hamilton constraint. So this is the 0,0 component of the Einstein equation if lambda equal 1 and CG equal 1, and but this is integrated over whole space, including our universe, other universe. So this doesn't tell anything. So we should forget about this. Okay. And on the other hand, momentum constraint and dynamic equation are local, so we should consider them. But this is just the 0I component of Einstein equation. This is IJ component of Einstein equation. Actually, we can find a general solution to these set of equations. Okay. Solution is this one. Okay. We can define additional term, and if we substitute this ansatz, or I mean, not ansatz, definition of this extra term. So this is a definition of this. Okay. By plugging this definition to these equations, we see that this component has a vanishing 0I component and a vanishing IJ component. So the solution to these equations is this. Okay. So this part should be proportional to n mu n nu, where n mu is a vector perpendicular to constant term surface. This is general solution. Okay. And actually, we can show that n mu satisfy the geodesic equation. So this looks like a stress energy tensor of dust or dark matter. Okay, this is the energy density, and this n mu corresponds to the 4 vector of dark matter element. Okay. And we have a global Hamilton constraint which sets the integration of this to be 0, but this doesn't tell anything about our universe, because this integration is integration over whole space, including our universe, other universe, everything. So we should forget about this. But we can have a kind of conservation equation. Okay. So by taking a divergence of this equation and using the Bianchi identity and the conservation equation for matter, we get the conservation equation of this. Okay, this is given by this. We get this. Okay, this is perpendicular. I mean, the perpendicular is a derivative with respect to along this vector. Okay, so this is the standard conservation equation of dark matter, cold dark matter. Okay. So we have a Poisson equation from here, and a geodesic equation, and also conservation equation. All we need for cold dark matter. Okay. So but we don't have extra degree freedom. Okay. Actually, so we didn't add anything to Poincaré gravity. So this kind of dark matter is inside the theory. So this degree of freedom should be there in the theory. So let's try to count the number of degree freedom, physical degree freedom. Okay. So we now have a lapse which is function of time. So this is not the field in space. So let me go back. Yes. So yes, sorry. Yes. So lapse is function of time. So this is not the field in space. So we have just a shift and a 3D metric. So 3 component and 6 component. So we have 9 components of the metric. Yes, yep. So 9 components. And if we go to the phase space, we should multiply by 2. This is the number of phase space before taking account the constraints. Okay. And we have a spatial diffeo. So we have constraints associated with the spatial diffeo, first class, and also the pi I, which are conjugate momenta, a momenta conjugate to shift. They are also first class. Okay. So we have 6 first class constraints. Each of them remove 2 phase space dimension, so that we end up with 6 phase space dimension at each point. Okay. Then we have 3 degree freedom. Okay. 3 is 2 plus 1, and the 2 corresponds to tensor graviton plus and the cross modes of gravitational waves. We have additional scalar. Okay. This is often called scalar graviton, and actually this is the origin of this dark matter. Okay, and so there are some debate about scalar graviton in this projectable positivistic gravity. So I want to spend some time to explain this. Okay. So indeed, if we send lambda to 1, then we may recover in the IR the general relativity plus dark matter. So the GR part is carried by these 2, and the remaining 1 is responsible for dark matter part. Okay. And projectable positivistic gravity has a scalar graviton in addition to tensor graviton, as I explained. So that this extra 1 is responsible for this. And what happens to the scalar graviton in this limit? Okay, this is what I want to discuss. Actually, this turned out to be very similar to what happens to massive gravity. In massive gravity, there was some breakdown of linear perturbation. So the perturbative expansion breaks down. So we need to take into account nonlinearity. If we do that, the continuity is recovered. So that we have continuous massless limit. We have something similar. Okay. So before that, I want to explain a bit about the linear instability of scalar gravity at low energy. Okay. At high energy, there is no instability, but at low energy, there is instability. Okay. First, if we compute second order action for scalar graviton around the Minkowski background, we see that the kinetic term is of this form. So we should have positivity of this. Otherwise, we have a ghost and the theory does not make sense. So we should have positivity. So this means that lambda should be larger than 1 or smaller than 1/3. But we want to recover lambda equal 1 at low energy. So we should consider lambda larger than 1. Okay, at high energy. Then lambda may hopefully goes to 1 at low energy. Okay, that's a hope. And then we can compute the dispersion relation for the scalar graviton in the flat background. It turns out to be like this. And so this coefficient it corresponds to the sound speed square. And indeed, this turned out to be negative. because this is exactly the same as this. Okay, and so maybe this is inverse of this. Maybe yes. Actually, there may be type. Yes. Yeah, actually, this is yeah, denominator and the numerator should be opposite. Yes. But anyway, the lambda should be larger than 1. Okay. And so this is negative. So at low energy, we have instability at the linear level. But this can be slower than gene instability if we have gene instability because the dark matter are coming from this theory or other matter sector or other kind of particle dark matter, whatever. So we need gene instability to explain the structure in the universe. And so if this instability is slower than this good instability, gene instability, then we can forget about this instability. And time scale of standard gene stability is like this, where rho is energy density. And time scale of this guy is like this, where L is a length scale of interest. Okay. And also this instability can be tamed by expansion of the universe if time scale of the expansion is shorter than the time scale of this instability. Or we can, if we have a higher derivative terms, and indeed we have, and the suppression scale is m, and if length scale is shorter, if we go to the shorter and shorter scale, then indeed the higher derivative terms become important, so that this instability disappears. Okay, so either this case or this case, instability does not show up. Therefore, linear instability does not show up if this condition is satisfied, where phi is basically Newtonian potential at the point of interest. Okay, and for L larger than this value. Okay, if L is shorter than 1 over m, then the higher derivative term kicks in and the instability disappears. Okay, if L is shorter than 0.01 millimeter, then we don't know what's going on there. So so it's totally consistent, even if we have a linear instability. As far as at the nonlinear level, it is stabilized. Okay. So this is something similar to space-time form. Okay. And so this can be considered as a phenomenological constraint on the property of RG flow. So when we consider quantum corrections and RG flows, the RG flow should satisfy this condition in order to be consistent with our universe. Okay. So this basically tells us that lambda is very close to 1 at low energy. Okay. At low energy, Hubble goes too small, and also the Newtonian potential is not too large, and then the lambda should be small, very close to 1. What happens if we send lambda to 1? Something very similar to Weinstein screening happens. Okay, so let's consider part of the expansion of this theory. So lapse is said to be 1 because originally, I mean, from the beginning, lapse is function of time. So by choosing time properly, this can be said to be 1. Then we can consider a shift as a perturbation, a scalar part and the vector part. And so this is the divergence free. And metric is decomposed into the scalar part and the tensor part. But this is fully nonlinear definition. Okay. And then we consider theta and h and b and n and perturbation. Sorry, theta and h as perturbation, but we try to solve b and ni as fully nonlinear way. Okay, we try to do that at least. Okay, it's very difficult technically, but let's consider them as order 1. Then the momentum constraint leads to this expression. Okay, this is perturbation, but in the denominator we have something like this. Okay, so when lambda is different from 1 by order 1, so this is order 1. So for small perturbation, when Q is small, then we can forget about this. And so the B is at the linear order because this is linear order. Okay, so when lambda is so the lambda minus 1 is order 1, we are in the perturbative regime. Okay. But when lambda close to 1, this breaks down. Okay. For a given value of Q, if lambda minus 1 is smaller than this, then so we have a perturbation divided by perturbation. So B becomes order 1. So this is this shows that the perturbative expansion completely breaks down. This is very similar to what happens in massive gravity in the mass regime. Okay, and so in this regime where lambda is small, so lambda minus 1 is small, we need to take into account nonlinearity. And this is responsible for recovery of GR, actually GR plus dark matter. This is very similar to massive gravity. Okay. So in this paper, I think we discussed about, we consider the nonlinear cosmological perturbation by using the so-called gradient expansion method. So the price to pay is that we need to consider large scale perturbation. Then we can consider nonlinear perturbation, fully nonlinear, with respect to amplitude. Okay. Then we consider Hodge-Elistic gravity plus scalar matter field, then flat Friedman background plus nonlinear cosmological perturbation at a large distance. Okay, large spatial scale. So we employ the gradient expansion method up to any order, and then we show that the solution is completely regular and continuous in the lambda to 1 limit, and we indeed recover GR plus dark matter plus scalar field that was introduced here in this limit. Okay, so the limit seems to be continuous if we take into account nonlinearity, very similar to Weinstein screening. Okay, so this is just a review of the Weinstein screening that we discussed before, and so something similar happens here.
Shinji,
so
sorry, Shinji. How far are you from the summary?
Yes, so I need to go. Yes, right. So I don't have time. So let me speed up.
Yeah, I don't know. I think it would be nice to leave some time also for questions. So if you wanted to summarize your lectures, maybe it's a good.
Sure. Yes. But is it possible to talk about cosmology in 5 minutes?
Yeah.
Okay. So let's finish this part. And so here I show that at the limit, in the limit lambda to 1 limit, we recover GR, and yes, GR plus dark matter. Okay. So the GR is recovered in the lambda to 1 limit due to nonlinear effects. Okay, so let's consider some cosmology. There are many interesting phenomena, but here I'd like to talk about, first I'd like to talk about this. So this theory can actually has a natural mechanism to solve the so-called horizon problem and leads to almost scale invariant cosmological perturbation without inflation. I'd like to talk about this. The question that I want to ask here is this one: where are we from? This is, I mean, we know the answer, of course. The answer is primordial fluctuation. Okay, primordial fluctuation evolved, and the galaxy and everything was created from primordial fluctuation. With respect, regarding quantum, this primordial fluctuation, there are 2 problems: horizon problem and the scale invariance. Okay. So if you look at the CMB, cosmic microwave background, we see that the correlation length that we observe is much larger than the scale of horizon at the decoupling when the CMB was created. Okay, so we need to explain how this kind of correlation length was created. And also when we look at a spectrum, it turned out that spectrum is almost scale invariant, and we need some reason why this is scale invariant. Okay. In usual story, we need to, usual story leads to inflation, usually. Okay. So when we consider large scale fluctuation, we consider a homogeneous isotropic universe plus perturbation, and perturbation is decomposed into a Fourier mode, and each Fourier mode is characterized by frequency omega. Okay, and if frequency is much larger than expansion rate of the universe, then that mode just oscillates. And On the other hand, if the frequency is much lower than expansion rate, then the mode is freeze out. Okay, freeze. Okay, so the because the friction, mode cannot oscillate, just stop. Okay, the creation of large scale fluctuation is nothing but oscillation followed by freeze out. So we want to have this after this. This can happen if and only if right hand side divided by left hand side is an increasing function of time. Okay, so the time derivative of this should be positive. Okay, if we plug usual dispersion relation, omega square is proportional to k square divided by a square, as the universe expands, the physical moment becomes smaller and smaller. That's why we have a square here in the denominator. By plugging this here and the definition of h here, then we get this definition, this condition. Second derivative of a scale factor should be positive. Namely, acceleration of the universe should be positive. This is nothing but inflation. Acceleration during early universe is inflation, basically. Okay. Scale invariance also suggests the inflation. So as we have learned, the scaling dimension of a scalar field, if you consider scalar field, is the same as energy. So as we change energy scale, the amplitude of quantum fluctuation of scalar field scales like energy. In the expanding universe, energy scale is given by an expansion rate of the universe. So the amplitude should be proportional to h. And it must be constant in scale, but in different scale, long scale and short scale. But during inflation, the large scale mode was created at early time. So that because if fluctuation was created early time, then there are lot of time to expand. So that corresponds to large scale. Okay. If the fluctuation was created at late time, it doesn't have a long time to expand. So it corresponds to short length. Okay. So they must have the same amplitude. That is what is required by scale invariance, meaning that the amplitude should be constant. H should be constant. If H is constant, then the setting this to be constant, we have exponential. That is inflation. We have inflation. Okay. On the other hand, in the new theory with z equals 3, namely Hojia-Ulrich gravity, we have totally different story. We need oscillation followed by freeze out, namely this condition, but the dispersion relation is different. Okay. By plugging this to here, we get this condition. This is satisfied even if A is T to P, where P is larger than 1/3. We don't need P larger than 1. Namely, we don't need accelerated expansion if P is between 1/3 and 1. Also, scale invariance is automatic because we have learned that the scalar field doesn't have a scaling dimension. So this amplitude is independent of energy scale, namely the constant, even if we change the Hubble scale, Hubble expansion rate. So the scale invariance is automatic, even if Hubble parameter changes, Hubble expansion rate changes. Okay, and both generation of large scale fluctuation and the scale invariance do not does not require inflation in the new case. Okay, so that also the tensor perturbation can be generated in a similar way, and this is a picture. Wavelength goes like this as the universe expands. This is a log scale in log of scale factor. This is the size of the fluctuation. It goes like this, and at late time, sound horizon agrees with the Hubble horizon. So it goes like 1/h. But in the early universe, the sound horizon is controlled by higher derivative terms and goes like this. So if the P is between 1/3 and 1, we don't need accelerated expansion, but still exits the horizon, enter the horizon. So we have something similar to inflation without inflation. Okay. So we have new quantum gravity. So we have a new mechanism of prime order fluctuation. We can solve the horizon problem and the scale invariance guaranteed. And you can introduce a slight scale independent. And also it predicts a relatively large non-gaussianity that may be detected in the future. Okay, I think I'll skip the other implication like solution to the fluxness problem, but the idea is similar. Z equals 3 scaling may automatically lead to flat universe. Okay, so let me stop here and let me summarize. Okay. Maybe I stop here. Yes, let me show what I already showed here before yesterday. So there are, in order to go beyond general relativity, because of Lovelock theorem, we need to break the assumption. We need to consider either extra dimension, extra degree of freedom, Lorentz violation, or non-Riemannian geometry. And we have many arenas to explore. It would be great if some of you can solve some mystery in the universe, or can construct quantum gravity, or can tell us more about GR by considering modified gravity. Okay, thank you very much.
Thank you, Shinji. It was a beautiful lecture. We have already a question from Gaston.
No, we're just clapping. Thank you.
Sorry. You're right. So there is some little time for question. So about Horowalitz's theories, I guess that dropping Lorentz invariance leads to a very strong observational constraints. What is the strongest constraint on this theory so far?
I think this one. Yeah, there are many. Yeah. So one, in the gravity sector, we need to realize that the speed of gravitational waves should be equal to speed of light. Yes. And this is controlled by coefficient of the 3D curvature. And so we need to find the IR fixed point with of the RG flow with this property. And also lambda should go to 1. That is a strong constraint. And also in the matter sector, at high energy, we expect to have a Lorentz violation because of the exchange of graviton. Okay. Gravity sector is Lorentz violating, so the matter sector also have a Lorentz violation, at least at high energy. And we want to recover Lorentz invariance at low energy. And that is also a challenge. And as I explained a bit, so there is a hope to find the IR fixed point, and probably IR fixed point with Lorentz invariance. That is probably generic, but if we don't do anything, then I think the speed approaching to such an IR fixed point is very, very slow, too slow to be consistent with observation. So we need to speed up to match with the observation and experiments. And there are several ideas, but still not yet explored fully. Yeah. So that is open questions.
Other questions? Zakaria?
Yeah, so thank you very much for all these nice lectures.
Thank you for listening.
I have a question about, for example, if you want to see deviation from general relativity and so on, can we consider the scalar field, for example, for Henri black holes, the same as the one responsible for dark energy? Because I have remarked the split between two community working on black holes, considering the scalar field just part of the black hole, and they don't want to interpret it like a dark energy. And the other community for cosmology, taking account this scalar field as dark energy. So is there any reason to consider that this scalar field is the same? And if it's the case, so on which kind of theories you can find good, stable Henri black hole solution, and in the same time, it may have cosmological relevance. For example, in Hrodensky, I didn't find anything. There is not a proof for there is claiming, even from the paper of Pedro Ferreira. But I don't know if in other theories, for example, generalized Procca theories, or in this new theory of massive gravity, or even in Java gravity, if there is a hope to find Henri black hole solutions that may have a cosmological relevance.
I see. Yeah. So indeed, each problem is namely the black hole, finding an interesting black hole solution and finding an interesting cosmological solution. Each problem is very interesting and important, and also not easy. So I think people try to find a solution to each solution, each problem. Then hopefully we may consider both of them. And but if we consider, for example, this, let me go back, minimal theory of bigravity, I think we can find this is not yet explored, but I'm sure that we can find interesting cosmology and interesting black hole solutions. I'm almost sure. And then yeah, even in the massive gravity case, we find that the cosmology is interesting, and black hole solution in the case of massive this empty minimal theory of massive gravity, spherical symmetry solution in the self-isolating branch is the same as GR, but in the normal branch, other branch solution, even with the spherical symmetry, I think deviation from GR should be there. And if we consider rotating solution, I think Kerr solution is not a solution. Indeed, because in this case, yeah, so it is known that for Kerr spacetime, we cannot find even conformally spatially flat slicing. And so so of course there is no spatially flat slicing for the Kerr geometry. So that this kind of lemma does not apply. So probably Kerr black hole in this minimal theory massive gravity, not rotating black hole is different from Kerr. And probably something similar may happen to bigravity case. Yeah.
And what about Hordensky and beyond Hordensky? Like, can you find other black hole solutions that may have?
Yeah, I think
because the existent one, like there is Einstein Day-Latin corresponding gravity and Einstein scalar,
right. Yeah,
and scalarization, but they are not relevant cosmologically.
Right. Yeah. So I don't know. Yes. So far I don't know, but only interesting solution is something that has kind of, so in a sense, Lorentz invariance is enforced by theory. So something like say square root of d mu phi square, minus d mu phi square is there in the some term in the denominator or something like that. So I think Einstein-Gauss-Bonnet, scalar Einstein-Gauss-Bonnet is one of them, I think. And so, but I think there's no go theorem. So there may be a hope, but I know it's not easy. Yeah.
Okay, thank you.
Yeah. But maybe some audience, if you know some example, please let me know.
Other questions?
Just what about generalized Broca theories?
Yeah, so I think generalized Broca theory reduced to either Horndeski or beyond Horndeski in the scalar sector. And so if you want to find something different from scalar tensor, from the, so then I think we need to turn on the vector sector, namely the transverse part of the vector. And I'm sure maybe rotating solution may be interesting. Yeah, but not sure. Yes, there are some solutions, but yes, I cannot guarantee. But one possibility, one direction to go, maybe to consider rotation. Anyway, something that turn on the transverse vector apart. Yes.
Okay, I think we can stop here. Thanks again, Shinji, for your very beautiful lectures. And maybe if there are other questions, we can collect them and hand them to Shinji.
Sure.
Okay, so we will resume this afternoon at 4 Central Europe. Okay, thank you.
Okay. Thank you very much.
Thanks to you.
Bye-bye.
Bye.
On peut arrêter l'enregistrement. On peut arrêter l'enregistrement. Eric, peut-être tu peux arrêter parce que tu es encore, je sais pas. Ah, je t'entends pas parce que tu es muted.